By considering the gradients of two lines, explain why arctangent of 2 minus arctangent of negative half, okay, is equals to pi over 2 radians or 90 degrees. Okay, of course we know that if two lines are perpendicular to each other, right, then the product of their gradients should be equals to negative 1. Okay, and as you can see, 2 times a minus half would give you a negative 1. Okay, and of course the tangent of the tangent means the gradient, right, and this is 90 degrees, right? So but let's see how to prove this in order to get that 1 mark. Okay, first let's make a sketch of this so that we can see, okay, you can see what I'm talking about. If let's say if I were to sketch the line y equals to 2x, right, so for this line the gradient of this straight line which passes through the origin with the gradient of 2, the gradient is of course a 2. Now what is the meaning of arctangent of 2? Arctangent is this angle here, right? So this angle here is actually, okay, rise over run, or change in y over change in x, okay, which is of course opposite over adjacent, and that should be equals to the tangent. So the angle, if you want to find, you just simply take arctangent of the gradient. That would give you whatever the angle is from the x-axis to that particular line. Okay, so that would be of course the first quadrant angle. So this is arctangent 2 is the angle from the x-axis to the line, right? Now let's draw another line whose equation is y equals to negative half x. So y equals to negative half x has got a gradient of negative half. So of course it's a negative gradient, so it will be a downslope line. And once again, if we want to calculate this angle here, okay, this angle from the x-axis to the line, it should also be arctangent, okay, of negative half. Okay, but of course this is the fourth quadrant angle, which is actually negative angle, right? Because it is, if you're going this way, it's negative angle. So we know that if I take two lines, okay, that are perpendicular to each other, and if I multiply the gradients together, it should be equal to negative 1. So m1 times m2, the gradient 1 times gradient 2. Gradient 1 here is 2, gradient of this line is a negative half. So if I were to multiply these two together, it gives us a negative 1, right? And when it gives the negative 1, since m1 times m2 is equals to negative 1, so what does it imply? It implies that these two lines must be perpendicular to each other. So if these two lines are perpendicular to each other, if I were to add this angle and this angle together, it should add up to 90 degrees, isn't it? So arctangent of 2, I'm going to add it to this particular angle, which is negative arctangent of negative half, right? And that should be equals to 90 degrees or pi over 2 radians. So of course now I can open up the bracket. So arctangent 2 plus minus is going to become minus. Arctangent of negative half is equals to pi over 2 radians. So that's why we have shown this. Okay, that's the reason why arctangent 2 minus arctangent of negative half is equals to pi over 2. So I want you to remember this, because in the next parts we are going to use this result as well. Okay, so the second part says, okay, the curves C1 and C2 have the equations which are given by 1 over x square plus 1, and another equation which is curve 2 has an equation of k over 3x plus 4, right? Both of them are reciprocal graphs respectively, where k is a constant and k must be bigger than 0, okay, which means k must be positive. Find the set of values of k such that these two curves C1 and C2 intersect with each other, and if you do that successfully, you will get 3 marks. So in order to find the value of k, and since we are told that these two curves intersect one another, we can equate, okay, the y with the y, alright? So 1 over x square plus 1 is equals to k over 3x plus 4, and the next step we are going to do is just to cross multiply. So of course k times x square plus 1, I'm just bringing the x square plus 1 across to the right side, and 3x plus 4, if I multiply it by 1, it's simply going to be 3x plus 4. Let us expand the bracket. So k times x square is a kx square, and k times a 1 is of course a k. And on the right hand side, okay, we have got a plus 3x. If I throw to the left, it becomes minus 3x, and a plus 4, if I throw to the left, it becomes minus 4, and it's equals to 0. And here we can see k and the negative 4, they are constants. So let's arrange this into a proper quadratic equations, okay, in descending orders, descending powers of x. So kx square is written first, followed by minus 3x. And then we have got the k and the minus 4. They are both constants, so I am writing it together. K minus 4 is equals to 0. Now, for C1 and C2 to intersect, if you want the two curves to intersect, the solution to this quadratic equation must be real, right? So, for solutions to be real, then the condition is the discriminant of this quadratic function, okay, should be positive. Okay, you know what I mean by discriminant. Okay, b squared minus 4ac must be positive. So b squared minus 4ac, which is the discriminant for this quadratic function, must be positive, so that, okay, the answers become real, the roots become real roots. And if the roots are real, then we know that this particular equation has got real solution, right? So b squared minus 4ac is greater than or equal to 0. So in this expression, the coefficient of x, which is negative 3, is the value of b. So minus 3 squared, then minus 4 times the value of a is of course k. So k times the value of the constant is k minus 4, because k and minus 4, they are both constant. So we're going to throw them here, k minus 4, and this should be greater than or equal to 0. It should be positive or 0. So now all that is left of us to do is to solve this inequality. Negative 3, if I square it, that's going to become positive 9. Minus 4k times k is going to give you minus 4k squared. Minus and a minus is going to turn the next term into a positive term. 4k times a 4 is going to give you altogether 16k, right? And this should be greater than 0. So if I were to multiply throughout the expression by minus 1, so minus 4k squared, and at the same time I rearrange them in descending powers of k. So minus 4k squared, if I times by minus 1, is going to become positive 4k squared, and plus 16k is going to become minus 16k, and plus 9 is going to become minus 9. And since I am multiplying the left hand side by a negative 1, of course the inequality sign has got to reverse, so you got to remember to do that. And of course 0 times minus 1 still remains as a 0. So there we have a nice beautiful quadratic equation. So all that we need to do is to factorize this quadratic equation and look for the value of k, which is positive. So because you are given in the question, k must be greater than 0. If I were to factorize this expression, or the quadratic expression, so we will have 2k plus 1 times 2k minus 9 should be less than 0. So now we can see, if I were to plot, function of k, okay, fk, okay, against k, so you're going to get a u-shaped parabola. So it's a 4k squared, so positive coefficient of k squared, and it's going to cut the k axis at k equals to negative half, and the other value would be k equals to 9 over 2, as you can see from the expression here, the factorized expression. So it's a u-shaped parabola, and you can see from this part we get k equals to negative half, which is this intersection or x-intercept. So the other value of k would be 9 over 2, which is the positive side of the expression. So this should be the now let's solve the inequality, right? So based on just this inequality alone, we know that for it to be less than or equal to 0, that means negative, okay, it can be anywhere between, the k can be anywhere between minus half all the way to, okay, positive 9 over 2. Then you can see it is fk is below the x-axis, which k axis, so we know that that would be negative. So k must be between, okay, minus half to 9 over 2, both inclusive. However, if you look here, k must be positive, right? So since k is positive, of course it has got to be only on the positive side of k, but it is not to include the 0, right? Because k must be bigger than 0, not equal to 0. So therefore this is the inequality as given, the restriction given by the question. So if we were to combine both of this together, we can see that k must be greater than 0 but less than or equals to 9 over 2. So that is the answer to the second part. Find the set of values of k such that C1 and C2 intersect. Let's now look at part 3. Okay, it is now given that k is equals to 2. Okay, so we have got a value of k, and we are told to sketch curve C1 and C2 on the same graph. That means using the same axis, given the coordinates of any points of, okay, where C1 and C2 crosses the axis, and as well as the equation of any of the asymptotes. So the C1 is of course y equals to 1 over x square plus 1. So let's just copy that down. So now let's sketch this. Okay, to sketch this I'm going to use a series of transformation of graphs. So we know that this is how the y equal to x square graph is going to look. So it's just a simple U-shaped parabola, and since there is a plus 1, so we're going to shift this graph up by 1 unit so that its y-intercept would be 1. So it's going to cut the y-axis at 1. So we have the graph of y equal to x square plus 1. Now all that we need to do is to draw the reciprocal graph of this. So of course this part is infinity, and when we take the reciprocal of infinity, it's going to become extremely a small number. Okay, so 0 plus, and the same goes for this side also. Is going to go to near the x-axis, so it will be just a small little positive value, and the reciprocal of 1 is going to be still 1, because 1 over 1 is still 1. So now that we can see the 3 critical points, so we can actually see how the shape of this graph is going to look. So that would be the shape of this graph, and there we have the sketch of y equals to 1 over x square plus 1. Now let's go on to sketching the curve C2, and we are told that to use the value of k, okay, as 2. So before we move on to curve 2, let's look at the axial intercept. Okay, so where does it cut the y-axis? It's cutting it at 0, 1. Okay, so that's your axial intercept, and the asymptote is basically the x-axis or y equal to 0, which is the equation of x-axis. So these are the couple of asymptotes, because the question asks and give the equation of asymptotes as well as axial intercepts. Okay, so now let's move on to sketching the curve C2. So C2 is y equal to k over 3x plus 4, where the k has to become now 2. So 2 over 3x plus 4. So let's once again do transformation. So this is the graph of y equal to 3x plus 4. We know it's a straight line graph, okay, passing through a y-intercept of 4 and having a positive gradient of 3. Okay, so of course this is how the graph looks like, right? And that value would be 4, and of course when y equal to 0 and we make x the subject, so it's going to be minus 4 over 3. So minus 1/3 is the x-intercept of this straight line. Now we need to draw the reciprocal graph of this, right? So of course wherever it cuts the x-axis, that's going to become the vertical asymptote. So x is equals to negative 1/3 is going to become the vertical asymptote. Okay, the reason being, if 3x plus 4 equal to 0, the function becomes undefined, right? So 2 over 0. So that's why, you know, when x is equals to negative 1/4, okay, the function is not defined, so that's why it's a vertical asymptote, right? And this part is infinity, and it is reciprocal is going to become extremely a small positive number, and this part is extremely a small number, its reciprocal going to go to the infinity. And the same thing is going to happen here. So this is a negative infinity, its reciprocal is going to be negatively a small number, 0 minus, and this is a negatively a small number, its reciprocal is going to go to negative infinity. So if we were to draw, okay, 1 over 3x plus 4, okay, we just need to draw the reciprocal graph of the straight line graph which we drew just now. Now it was cutting at it was having a y-intercept of 4, so its reciprocal would be 1 over 4. That's why the y-intercept now is 1/4, right? And this x-axis is of course one of the asymptote, and x equals to minus 1/3 is the other asymptote. So the axial intercept, before that, so but the graph we are given is 2, right? So we're going to scale it up by 2. So 1/4, okay, if I were to times it by 2, so it's going to go to half. So half is bigger than 1/4, so it's going to be maintain the same shape, except that the y-intercept is going to go slightly higher. So if you were to draw it, so the graph is going to look like this. So this is the purple graph is the actual curve C2, which is 2 over 3x plus 4. So there we have the graph. So we have drawn it both on the same axis. Now let's look at the axial asymptote, axial intercept. So y-intercept is at 0, half, right, which we can see here. And then the asymptotes, there are two asymptotes for this curve. Okay, the first asymptote is y equal to 0, which is basically the x-axis, which is here. And the second asymptote is x equals to negative 1/4, which is a vertical axis. So vertical asymptote. So x equals to negative 1/4. So these are the asymptotes. Now let's look at the next part, part 4. It says find the exact area of the region bounded by C1 and C2. Okay, between the two curves. Okay, as you can see here, this is the particular region, okay, where there is a particular region here which is bounded between the two curves, the purple graph and the blue graph. In the region that we want to find, we can see that the blue graph, which is actually your curve C1, is higher than your C2, right? So we're going to take this as the y2, or the above or upper graph, and this is going to be the equation of the lower graph, right? So now the x coordinates of the points of intersections is what we need to find, because we need to know from where right up to where we need to integrate so that we can find the area bounded between the two curves. So in order to find the point of intersection, right, so let's equate the two graphs, okay, equations of the two graphs, because we are only interested in the x intercept, I mean the x coordinates of each of the points. So therefore I can just eliminate the y, so I get a 1 over x plus 1, which is from the curve C1, and equate it to the curve C2, which is 2 over 3x plus 4. And then let's cross multiply. 2 times x square is 2x square, 2 times a 1 is of course a 2, and 1 times 3x plus 4 is simply going to be 3x plus 4. Now the next step is to throw it all over to the left side, so as to turn the right hand side equal to a 0. So we get a 2x square plus 3x. If I throw to the left, it becomes minus 3x. I already have a plus 2, and if I throw the plus 4 over to this side, it's going to become minus 4. So from 2 you subtract a 4, it's going to give you a minus 2. And since we have already brought everything to the left, so the right hand side is equal to 0. So there we have it. So the next step is to factorize this expression so as to find the two x-intercepts. So the factorization gives you one of the factors as 2x plus 1. The other factor is of course x minus 2 is equal to 0. So from this we can see that x is equals to negative 1 over 2, or x equals to 2, right? So x equals to negative 1 over 2, or the negative half, and the other solution would be x is equals to 2. So now let's sketch these 2 points, okay, or mark the coordinates here. So x is equals to negative half is over here, and x is equals to 2 is the x coordinate of this point, okay, where the two graphs intersect. So now we know from where to where, okay, we need to integrate. So area bounded is what we're going to find next. So we're going to use the formula y2 minus y1 dx and integrate it straight from negative half to 2. So what is going to be a y2? Y2 is whichever graph that is above. So in this case, you can see the blue graph is above the purple graph. So your y2 is the blue graph. That means we're going to put in the equation of this particular curve, okay, 1 over x squared plus 1 as my y2. So I'm going to put my y2 as 1 over x squared plus 1, and then from that I'm going to subtract the purple graph's equation, which is 2 over 3x plus 4 with respect to x. Now you will recognize that straight away this is actually a arctangent function, right? So 1 over x squared plus 1 is an arctangent function. So what I'm doing now is splitting it up first. So 1 over x squared plus 1 dx, I want to integrate it separately. And then the other one, I have 2 over 3x plus 4. I want to integrate it separately as well. So what I'm doing now is I'm just pulling out a 2 outside, okay, and in a while I will explain to you why there is a 3 here, okay. If I were to differentiate the denominator 3x plus 4, I know that I should get a 3. So I'm introducing a 3 as the numerator so that this particular integral is of the form f prime x over fx. So of course we know in the next step it's going to become ln of the function of x. So because I'm introducing a 3 here, so I put a 1/3 outside and 1/3 combined with the 2 which I pulled out, so it becomes a 2/3 outside. Hope you understand how I got that 2/3 over here in order to turn this into a 3 over 3x plus 4. Now you look at both of them, they are beautiful and they are easy to integrate, very easily integrable. So let us now continue with the integration. So the area bounded would be, if I integrate 1 over x square plus 1, okay, this one is straight away you can recognize this is arctangent of x, and of course now I write the limits outside, so I have already integrated this, so I need to substitute the limits of 2 to minus half in the next step. So let's go to this side. So the 2/3 I'm just going to keep it as it is, and this is of the form f prime x over fx. So simply it becomes, when you integrate it, it's ln of modulus of the function of whatever function that's found in the denominator, which in this case is 3x plus 4. And once again the limits are 2 to minus half to 2, right? So now let's plug in the limits, okay, since we have already integrated. This is going to become arctangent of the upper limit, which is 2, right? And then we're going to minus away the arctangent of the lower limit, which is a negative half, right? So there we have actually evaluated the first integral. Now we have got a minus and then a 2/3. Now let's plug in the values of 2 and minus half into the log function. So ln of 3 times 2, of course I'm replacing the x with the 2, plus 4. Then let's now substitute the lower limit, minus ln of 3 times, of course the x value I'm going to replace it with negative half, and then I've got a plus 4, which is what I have written here. Now if you recall from the first section, okay, this is what we did at the first part of the question, okay, arctangent of 2 minus arctangent of negative half. We have already proven this is equals to pi over 2. If you recall that, this was the very first part we did, okay, 2 and minus half, we used the tangents to prove it. So because these two lines were perpendicular, so that gave us the angle pi over 2 radian. And then we have got a minus 2/3. And then let's simplify this. Thrice of 2 is 6. 6 plus 4 is going to give you a 10. So we have a ln 10 minus ln 3 times minus half, okay, is going to give you minus 1.5. So from 4, if subtract the 1.5, that's going to give you 2.5. Now we can use ln a minus ln b. Of course, it's going to become ln a over b. So pi over 2 minus 2/3 ln 10 over 2.5. So which is simply going to become 10. If we divide by 2.5, that's going to be a 4. So we get a pi over 2 minus 2/3 ln 4, which is, you can simply write it as ln 4. You can express it as 2 squared, and then you can bring the 2 to the front and times by 2 to get a 4/3 ln 2. So there we have the complete area, okay, bounded by the two curves has been found, okay. So if you wish, you can evaluate it using the calculator.